Okay, so this is the arm model we're gonna use today. That's pretty cute. So that's simulate our upper extremity. So you can see got a tiny hand here and a movable upper forearm and upper arm. So we're going to adjust the angle of the elbow. So you can see the angle here from 0 will be horizontal and to probably 30, 60, and 75. And also we can put some weight on the hand. We got a tiny hand here. So on horizontal, which is 0 degree, we put like 50 grams on the hand. And then you can know how much force you need to generate from your bicep to maintain this posture. So you can see the weight scale is simulating our elbow flexor or our biceps. So it's simulating this kind of movement. Okay, so basically that's the equipment we're gonna use today. We got two weights, 50 and 100, and you add them together will be 150. So we got 4 weights, 0 and 3 weights to put on the hand, and several angles. So we can take a look at the manual. Let's take a look. Let's take a look at the manual. So we got 2 experiments. The first experiment is proximal attachment side, and we got 0, 50, 100, or 150 grams. And in different forearm position, that'll be 0 degree, 30 degree, and 60 degree. So what does proximal attachment side mean? Actually, we can simulate a quick tendon transfer surgery on this model. So we got a tendon attachment side here. We got 2 attachment sides, so it'll be distal one and the proximal one. So you got 2 attachment sides. So you can think about like we're actually changing the moment arm for your elbow flexor. So we can see like if you have a larger moment arm, what would change in your biceps force. So that we will start from proximal attachment side with 3 degrees, and for each degree we're going to put no weight and 3 weights on it. And we're going to record the force generated by your bicep and record it from at this column called FM. So that'll be proximal side, and also for distal side. 3 degrees, 4 weights, and also for experiment 2, we got more degrees. So that'll be 0, 15, 45, 75. And we're going to record the force with only 50 grams on the hand and the attachment side and the proximal and distal side. So that's what we're all going to do today. Fairly simple. And we just want to know like how does the moment arm of your elbow flexor affect your bicep force, and how does different elbow degree affect your bicep force. So let's have a little bit of free body diagram. So actually our bicep is generating force, but for the muscle to maintain the elbow posture, actually you need to consider the moment the muscle generated, which will be the force times the moment arm. Right? The force itself is not enough to describe the joint motion. So how do we calculate the moment? Actually, that will be force multiplied by moment arm. Right? And then in this simple case, that will be the force multiplied by the length of this black stick. But in this case, the force and the black stick is not like perfectly perpendicular. So actually for moment arm, it should be perpendicular to the force, right? And it should go through the axis of rotation. So actually in this case, the moment arm will become this R perpendicular, which is cosine theta of the length of the black stick, right? So that'll be D cosine theta would be our moment arm in this case. So actually, the moment arm is decreasing, right? From here to here, the moment arm is decreasing because you multiply by a cosine theta, which is always smaller than 1. Right. Okay, so let's go to today's setting. That's our model, the upper arm, forearm, and the hand is holding a tiny weight here. So the length of the forearm will be L, and there will be a degree theta here. So the first step to solve a free body diagram is to list all the forces. So the force will be the weight of your forearm, right? And also the weight of the object you're holding. So how do we calculate the moment in this situation? The clockwise moment generated by the weight and the weight you're holding and the weight of your forearm. That'll be this one, right? F times L cosine theta plus W times 1/2 L cosine theta, right? This is a clockwise torque generated by the weight you're holding on the hand. So that'll be F, which will be like 50 grams or 100 grams later in the lab. And also the moment arm will be L cosine theta, depends on the degree here. Right? L is not changing because that's the length of your forearm, but the angle is will be changing throughout the whole lab, right? So that's all the clockwise torque. And then for the elbow to maintain an equilibrium state, the counterclockwise torque should be the same as clockwise torque, right? So for counterclockwise torque, it's actually generated by the muscle itself. So that's the muscle, Fm. And how about the moment arm? The moment arm will be C in this graph. Right. So if we take a look at the force generated by the muscle, that'll be Fm, and the moment arm will be C. So the counterclockwise torque will be Fm times C. And in this case, clockwise torque should be the same as counterclockwise torque, right? Is everything good right now? So think about it. If we move the upper arm, if we move the forearm upper and upper and upper, what would be the corresponding change of bicep force? So for example, we have it holding this tiny weight here, 50 grams. From here, you got a bicep force, and then upper, you got another bicep force, and upper, you got another bicep force. How would you expect the bicep force to change? Would it go up or would it go down? We can think about the clockwise torque generated by the weight first, because the muscle force has to counter that force, right? The muscle moment has to counter that moment. So for that moment, the weight is not changing, right? But the moment arm is becoming smaller and smaller. So actually for the muscle, it doesn't have to counter that much moment when the angle increases. So we expect the muscle force to decrease with larger angle. Does that make sense? Okay, cool. So that's the concept. And I believe Dr. Smith has covered that, right? We got 3 kinds of lever class 1, 2, 3, right? Depends on if it's a force advantage or like range advantage. So actually in the model, that'll be which class? Yeah, that'll be 3rd class. So we have a smaller moment arm for our muscle than the load we need to counter. Right? So I think that's about it. Yeah, and so a little bit more about the muscle moment arm. Actually, it won't change a lot, but it'll start with a smaller moment arm, and when the angle increases, the moment arm can be the distance from the attachment side to the axis of rotation. That's the maximum it can get, and then it'll start to decrease later. So it'll increase and then decrease for the muscle moment arm, but actually it won't change a lot. So it really depends on the moment arm of the weight it's holding. So we can like ignore the moment arm of the muscle. So we expect the muscle force to decrease when you have larger angle. Yeah, any questions for now? No? Okay, cool. So we got 4 people. I think we're gonna work in 1 or 2 will be fine. Yeah, depends on you, because it's not a really hard task. So we got 4 sets, just find your table and finish 3 tables on the manual. That's all you need. And there are 12 questions for the lab, but usually it's not a hard one, I think.